Good morning everyone. My name is Dr. Manpreet. I'm working as an associate professor in Chandigarh Engineering College in the Department of Applied Sciences. Today I am going to explain the topic eigenvalue and eigenvector. In linear algebra, an eigenvector of a linear transformation is a vector that only change by a scale vector when the linear transformation is applied and the direction will remain unchanged. In general, when a matrix X on a vector, by changing its magnitude as well as its direction. And sometimes it happens when matrix X on a vector, then the direction will remain unchanged, but the only effect will be on the magnitude. These type of vector are said to be the eigenvector. So if we are explaining through the definition here, let's say if A is the matrix, A is a square matrix, and X be the eigenvector of A, matrix A, there is a condition that this must be an eigenvector here. Sorry, this is a square matrix and this is the eigenvector of A. If this condition holds, that is Ax is equal to lambda x. It means when matrix is multiplied with the eigenvector, then there is then the change effect, that is it will be scaled by the value, that is the value lambda. Now this will become the eigenvector if this condition holds, and this lambda is said to be the eigenvalue. Now in short we can say that an eigenvector is a vector that maintains its direction, that is the direction will remain unchanged, but the only change will reflect in the magnitude, and the lambda is the eigenvalue by which this eigenvector is scaled up when the linear transformation is applied. Now the next thing is how if we are looking for how to check whether this is an eigenvector or not. Let's say we are having this matrix, that is 3, 0, 8 and minus 1. We have to check whether the vector 1 and 2 is the eigenvector of this matrix or not. How to check it? We are just applying this definition. We are replacing the value of matrix A. This is 3, 8, 0 and minus 1. This will be the vector X, which we are supposed to check whether this is an eigenvector or not. This is 1 and 2. When it is multiplied, we will get the matrix as a 3 and 6. Fine. 3 and 6 will be the matrix. If we are plotting it on the graph, this vector, this is 1 and 2. 1 and 2 will be somewhere here. This is the vector. We are going to check whether this is an eigenvector or not. Once it is multiplied, we are getting 3 and 6. 3 and 6 will be here. Now we can easily observe the vector is scaled up, 1 and 2 will be scaled up, but the direction is unchanged. It will in the same direction. Because the direction is unchanged, so 1 and 2 will be the eigenvector of this matrix. And if we are taking mathematically, we are looking by definition. Then if we are taking 3 as a common, we are left with here 1 and 2. This is the eigenvalue by which the eigenvector will be scaled up. So this is the value, lambda is equal to 3, and this is the eigenvector of this matrix. Fine. Similarly, if we are taking another vector, then let's say 2 and 3. Matrix is remaining same. Let's plot 2 and 3 here. 2 and 3. Once we are replacing the value here, A is same. Replace the value 2 and 3. The matrix is multiplied and we are getting it as 6 and 13. Right? And if we are plotting it on the graph, 6 will be here, 13 will be somewhere here. Without any doubt, the matrix, the vector is scaled up, but it has changed its direction. Once it has changed its direction, so this is not an eigenvector. So this is the most important thing, that eigenvector is not changing the direction, only the change reflect in the magnitude. If the value of lambda is positive, that means the eigenvector is magnified, fine, and the value is negative. If the lambda is negative, that means the value is contracted. So by which value the eigenvector is scaled up, the value is known as the eigenvalue. The next thing is, similarly we can observe from the matrix of order 3, once the matrix is multiplied with this vector and the outcome will come out to be 3, 3, 6. If 3 is taken out, we are left with here 1 and 3. It means this vector is scaled up by which value? 3 value. So 3 is the eigenvalue for this matrix and 1, 1, 2 will be the eigenvector. So next thing we have understand the concept what is eigenvector and what is the eigenvalue. Now the next step is how to calculate the eigenvalue and eigenvector. For that we are going from the basic definition again. this is Ax is equal to lambda x. Just shift on the left hand side, this will become Ax minus lambda x is equal to 0. Take x common from here, we will get a minus lambda I into x is equal to 0. We have read the product of two terms is 0. Either the first term is 0 or the second term is 0. It means either a minus lambda I equal to 0 or x is equal to 0. But by the definition of eigenvalue and eigenvector, we have read that x is a non-zero vector. If x is non-zero, it means we cannot equate it to 0. This cannot be equal to 0, so it will be neglected. We are left with only term a minus lambda I equal to 0. Now, the very first step to calculate the eigenvalue is we have to calculate a minus lambda I, then take its determinant. Once we are taking the determinant and equating it to 0, we will get the characteristic equation here. Right? Characteristic equation giving you the eigenvalue. Depending upon the order of the matrix, we are getting the characteristic equation. It means if the matrix is of order 2, then we are getting the characteristic equation as a quadratic equation. If the matrix is of order 3, then automatically we are having a cubic equation. Right? Quadratic equation is giving you 2 roots and cubic equation is giving 3 roots. So it means if the matrix is of order 2, we are having quadratic equation and we are having 2 roots. Similarly, if we are having order 3, matrix of order 3, then we are having cubic equation and matrix and the roots will be the 3 roots. So this is the way to calculate the eigenvalues. The very first step is to calculate a minus lambda I, then calculate determinant of a minus lambda I, which is giving you equation depending upon the order of the matrix. Splitting the equation, we will find the roots and the roots are the eigenvalues of the matrix. The next step, how to calculate the eigenvector. We have already calculated a minus lambda I into x in this step. Fine. Replace each and every value turn by turn and parallel to each and every value we will get the distinct eigenvectors. So here are the some properties of eigenvalues. The very first property is sum of the eigenvalue of the matrix is equal to trace of the matrix. Second one is product of eigenvalue is equal to determinant of the matrix. The next one is eigenvalue of a diagonal matrix. Diagonal matrix means the matrix whose non-diagonal elements are 0. Let's say we are having a matrix 1, 0, 0, 0, 2, 0 and 0, 0, 3. This is the diagonal matrix. So its diagonal elements are 1, 2, 3. It means the eigenvalue of this matrix will be 1, 2, 3. Same rule will be followed for the triangular matrix. The next one is the lambda is the eigenvalue of A. Then the eigenvalue of A inverse is 1 upon lambda. They are the different proof for these one. We can simplify it. Let's say the very first we are proving here, if lambda is the eigenvalue of A and we are supposed to prove lambda inverse is the eigenvalue of A inverse. This is Ax is equal to lambda x. By definition, that is lambda is the eigenvalue of A and we are supposed to prove lambda the eigenvalue of A inverse is 1 upon lambda. It means we have to introduce A inverse in the question. What we will do, we will multiply both sides by A inverse. Now next thing, A inverse A will be the identity matrix. We have read in the lower classes. Now lambda is the eigenvalue, that is a constant value which can be taken out. So we will take lambda as a common out. Left with inside A inverse. Take lambda on other side, that is identity upon lambda. X is equal to 0, that is A inverse x is equal to 0. So it means identity multiplied with any vector will be giving you x. This is 1 upon lambda is equal to A inverse. This is what we want to prove. If lambda is the eigenvalue of A, then 1 upon lambda is the eigenvalue of A inverse. Similarly, we have different properties and we can prove this in the similar way. The next thing is how to calculate the eigenvalue and eigenvector. We are taking the simplest example, that is the matrix of order 2. So let's start with the matrix of order 2 here. We will follow the same step which we have discussed the way first thing is we will use the basic definition. Ax is equal to lambda x. Shift the term on the other side, that is ax minus lambda x is equal to 0. Take x as a common. We are left with here a minus lambda I into x is equal to 0. Right? Starting from here, the way first thing is we have to calculate a minus lambda I. So this is the A matrix. The very first step we will calculate a minus lambda I. So the a minus lambda I will be 2 minus lambda minus 12, 1 and minus 5 minus lambda. Now we have to take the determinant. Take the determinant of this term. Because the first step to calculate the eigenvalue is calculate a minus lambda I. The second step is to take its determinant and equate it to 0. Once we are calculating the determinant, how to calculate the determinant? This will become 2 minus lambda. The next will be minus 5 minus lambda and this will be plus 12. After simplifying it, we will get the equation here lambda square plus 3 lambda plus 2. Now we have to equate to 0. Fine. The matrix is of order 2. We get the quadratic equation. Obviously, quadratic equation is giving us the two roots. So split it out, splitting the roots equation, we will get the root as minus 1 and minus 2. This is what? Now these are our eigenvalues for this matrix. Fine. This is the characteristic equation. This is the eigenvalues. Now the next step is to calculate the eigenvector. How to calculate the eigenvector? We will start from here. We have already calculated a minus lambda I. Put the value lambda is equal to minus 1 here. So put lambda is equal to minus 1 here. Once we are putting lambda is equal to minus 1, put lambda is equal to minus 1 here. If we are putting lambda is equal to minus 1 here, we are having here 3 minus 12. The next will be 5. Again put lambda is equal to minus 1 here, we are having here minus 4. Fine. Now we have to choose x. How to choose x? X is a column matrix. Firstly we are writing here column matrix. Depending upon the order of the matrix. Order of the matrix is 2. So the order will be 2 here. This is a column matrix. The very first thing is because the order is 2. So we are writing it 2 cross 1 matrix. We are taking it as x and y. You can write x1, x2 also. You can take x, y if you wish. Replace the value of x here. Put x here. Now we will multiply these two matrices. If we will multiply, this is giving you 3x minus 12y equal to 0. The next will become x minus 4y equal to 0. Fine. Here the equations are similar equation. Once we are taking 3 as a common from here, both the equation will become similar. So taking the bottom one, x is equal to 4y. Fine. Put any constant for y is equal to k, which is giving x is equal to 4k. Replace the value here, x is 4k and y is k. Because the eigenvectors are always linearly independent corresponding to distinct eigenvalues. So what we are doing, we are taking k as a common from here. Take k as a common. We are left with here 4 and 1. So 4, 1 is the eigenvector corresponding to which value lambda is equal to minus 1. So lambda is equal to minus 1. We are having 4, 1 as a eigenvector. We can simplify it for lambda is equal to, the next value is minus 2. We will follow the same step. We are taking the value lambda is equal to minus 2. Put in a minus lambda I because this is a step to calculate eigenvector. Fine. We are replacing the value lambda is equal to minus 2. Put lambda is equal to minus 2 here. We are having 4 minus 12. The next one is here. This is giving you minus 3. The value of x will remaining same. To put the value of x here, this is x and y. Multiply the two equation. This is 4x minus 12y equal to 0. Since again here both the equation are similar. Once we are taking 4 as a common from the first equation. Fine. So the equation here we are having x is equal to 3y. Take y as equal to k here. So it is giving you x is equal to 3k. Replace the value here. If we are putting here x is 3k, y is k. So once we are taking k as a common, left with inside 3, 1. Fine. So corresponding to the value lambda is equal to minus 2, we are having 3 and 1. Fine. For just for cross checking, you can check the first eigenvector and the second eigenvector, that must be linear independent, because the eigenvector corresponding to distinct eigenvalues are always linear independent. You can check. We have already read these topics in the previous concept of linear independency and linearly independent. Fine. So this is the way to calculate eigenvalue and eigenvector. Again, briefing it out. The very first thing is we are calculating A minus lambda I. The second step, we are equating it to, taking the determinant and equating it to 0. The equation giving you as eigenvalues and replacing each and every eigenvalue turn by turn in A minus lambda into x equal to 0, giving us the eigenvectors. Fine. This is the one way. There is another shortcut to find the characteristic equation. Sometimes it happens once we are having determinant of order 3 or of order 4, then a student find difficulty in calculating the determinant. So there is another way to calculate the determinant, calculate the characteristic equation. Method is, if we are having matrix of order 2, the one method is to calculate the characteristic equation by determinant of A minus lambda equal to 0. Right? And the another way is, because this is a matrix of order 2, so it is giving you a quadratic equation, lambda square minus trace of the matrix. We have discussed in the property, trace is the sum of the diagonal elements. So lambda plus determinant equal to 0. So if we are checking for this matrix, we are having here lambda square. What will be the trace? Trace means the sum of diagonal element 2 and minus 5. 2 and minus 5 will be minus 3. Plus determinant. Take the determinant minus 10 plus 12, which is giving you 2. Right? So the characteristic equation will become lambda square plus 3 lambda plus 2 equal to 0. So you can calculate the characteristic equation by any of the way. Either you can calculate by taking the determinant of A minus lambda I, or you can calculate by this method. You have to learn this trick once you are having matrix of order 2, and once we are having matrix of order 3, then the way out is matrix is of order 3. That means we are having a cubic equation here. So if we are having matrix of order 3, then the characteristic equation will become lambda cube, because this is the cubic equation, minus, here is the trace of the matrix, that is sum of the diagonal elements, or you can write it as A11 plus A22 plus A33 lambda square. The sign will be alternately positive, negative sign. This is negative. So the next turn is for positive sign. This is the minor of the diagonal elements, M11 plus M22 plus M33 lambda. Again positive sign, alternatively now this is a negative sign, and the determinant of the matrix. So this is the way to calculate the characteristic equation of matrix of order 3. Either you can go for this method, or we can go for the basic traditional method, that is determinant of A minus lambda equal to 0. So if we are looking for this matrix, this is a matrix of order 3. So we are replacing the value here. This is the sum of the diagonal elements. Sum of the diagonal element means minus 2, 1 and 5. This is giving you 4. So you can write here 4. This is 4 lambda square. Now minor, I think everybody know how to calculate the minor. I am explaining the one only. If we are calculating M11, that is minor of this element, minus 2, that means corresponding column will be eliminated, corresponding row will be eliminated. We are left with here 1, 2, 2 and 5. Take the determinant, we will get here 1. So the minor of 2 minus 2 will be 1. Similarly, we can calculate minor of 1 and minor of 5. Replace each and every value, we will get the characteristic equation. This is lambda cube minus 4 lambda square minus 27 lambda. Take the determinant of order 3. We have already read, this is plus 90 is equal to 0. This is giving you a characteristic equation. Now we have to find eigenvalues. It means we have to find the root of this equation. Because this is a cubic equation, we don't have any direct rule for this. We have to go for the hit and trial for the very first rule. So by hit and trial, we will find the first rule. What do you mean by hit and trial? We will put the roots turn by turn, and left and right side must be equal. We are putting lambda is equal to 1. That's we are not having. Put lambda is equal to 1 here. We are having 1 minus 4 minus 27 plus 90. This is not equal to 0. So that means lambda is equal to 1 is not satisfying this equation. Similarly, we can try for lambda is equal to 2 then. Putting lambda is equal to 2. Again, both sides are not equal. That means this is not satisfying this equation. Now, the last we have tried for lambda is equal to 3. If we are substituting lambda is equal to 3 here, you can check it out yourself. If we are putting lambda is equal to 3, then both sides are equal. That means lambda 3 is satisfying this equation. So the first root for this equation will be lambda is equal to 3. But this is a cubic equation. We have to find the 3 values. This is giving you 3 values. The rest values will be either you can calculate it by long division, which we have read in the lower classes, because 3 is the root of this equation. You can do the division here. Fine. But here I am going to explain the another method, that is called the honors method. This is a shortcut method to find the roots of the equation. The first root by default will be find out by hit and trial. The rest root will be find out by this honors method. Okay? This rule will be applied for cubic equation as well as for biquadratic equation, even for the higher order equation also. Right? So the rule will be followed like this. The rule is this. The first root which we have find out by hit and trial. Write it here. Now pick the coefficients of the equation. That is this equation. The coefficient will be 1. The next coefficient will be minus 4. The next coefficient is minus 27. And the last will be 90 here. Right? The most important thing is we have to start from the ascending higher power, then going for the lower, and the constant term. Right? Write the coefficient only. This is 1, minus 4, minus 27 and 90. The rule is saying whatever be written on the first term, if it is 1, write here 1. If it is 2, write here 2. If it is minus 1, write here minus 1. We are just copy pasting the first term. Because this is 1, I have copied it here as 1. Fine. Now, we multiply these two terms. This is 3 into 1. 3 multiplied by 1 will be 3. Write here 3. Fine. If you can observe, this is giving you a sign of multiplication. So, we are just multiplying from this side. So, this is 3 into 1. 3 into 1 will be 3. Write here 3. The next will be, if we can observe, this is a sign of addition. So, we will add here minus 4 plus 3. This is minus 1. Again, from this side, we are just multiplying. So, if we are multiplying from here, this is 3 into minus 1, which is giving you minus 3. From this side, we are doing addition. Addition means minus 27 minus 3 is giving you minus 30. Now this side we are doing the multiplication. So if we are multiplying 3 into minus 3, 30 is minus 90 and this is 0. Because we have added from this side 90 minus 90. This is 0. So once we are doing the long division, at the last we are having the remainder, that is basically 0. Cross dalte hain. This is the remainder 0. If we have choose the right root and even we have do the right calculation, then by default this remainder must be 0. If it is not 0, then there is some mistake either in finding out the root or in doing the calculation. So I am explaining the honors method once more. First take the coefficients. Fine. This term will be copied up. Now we will do the multiplication from this side. This is 3 into 1 will be 3. Minus 4 plus 3 will be minus 1. 3 into minus 1. This side we are doing the multiplication and from this side we are doing the addition. This will be minus 3. Add these terms. This will be minus 30. Again multiply from this side minus 90 and this is the remainder which is 0. So this was a cubic equation. One root we have found out by hit and trial. The rest will be found out by here. Now by default this is a cubic. एक root हमने find out कर लिया. The last we are left with here. This will be a quadratic equation. How to write the equation? These are the coefficients. We have started from the coefficient. The last will be again the coefficient. This will be lambda square minus lambda minus 30 is equal to 0. How we have written quadratic equation? The coefficient is 1. Linear term, 1 less power. This is minus 1 and the coefficient here is minus 30. Split it out. After splitting it out, we are having here minus 5 and 6. Fine. One root we have taken as 3. We have find out by hit and trial. And the remaining roots we have got minus 5 and 6. Because this is a cubic equation. So the roots we are having here 3, minus 5 and 6. Now we have find out the eigenvalues. But we have to find the eigenvectors now. How to find the eigenvectors? So let's start here. we have to put each and every term turn by turn where in a minus lambda I into x, right? So let's calculate a minus lambda I first. As we have already talked about, this separation will only affecting the diagonal elements, right? So the remaining element will be same, minus 2 minus lambda minus 4 2 minus 2 1 minus lambda 2 4 2 5 minus lambda. You can easily observe the only diagonal element is affected. Remainings are same. So this is a minus lambda I have just written it here because for each and every eigenvalue, once we are finding the eigenvector, we are using this term, fine. So the first thing is lambda is equal to 3. Replace the value here. Lambda is equal to 3 here. We are doing this process for lambda is equal to 3. Put the value here. Lambda is equal to 3. So this will be minus 5, minus 4, 2. The next will be minus 2. Put it here. This is minus 2 and 2. This is 4, 2 and 2. Now choose x. X is a column matrix. This is column matrix. Order of the matrix is 3. So we are taking it as x, y and z. You can take it as x1, x2 and x3 also. Multiply by equation minus 5x minus 4y plus 2z is equal to 0. The next will be minus 2x minus 2y plus 2z is equal to 0. The last will be 4x plus 2y plus 2z is equal to 0. Right? There are the different ways to solve these system of equation. We have read in the lower classes. You can solve it by rank method or you can solve it by matrix method also. But here we are applying another trick here. Not a trick, there is an old method we have read in the lower classes. The rule is known as the cross multiplication method, and some students are knowing it for 2 3 1 2 method. Okay? The name is 2 3 1 2 or cross multiplication method. This rule is applicable once we are having the distinct equation. You can observe each and every equation is distinct here. You can take any of the two equations. I am taking the bottom one. Fine. I have taken the bottom two equation. What do you have to write? This is 2, 3, 1 and 2 here. Fine. This is the first variable, this is the second variable and this is the third variable. So 2 stands for the second variable. Second variable here is y. Pick the coefficient of y. This is minus 2 and minus 2. Right here minus 2 and 2. Fine. 3 means the third variable. Which is the third variable? Z. So take the coefficient of z here. Thus it's 2 and 2. Again 1 means the first variable. First variable is x. So take the coefficient of x. This is minus 2 and 4. Right here minus 2 and 4. This is a repeated one. Minus 2 and 2. Right? But we have to find the value of x, y and z. How to find the value of x, y and z? 2 means second variable. 3 means third variable. Which variable is missing from here? The first one. So the first variable is x. Right here x. Similarly here 3 means the third variable. 1 means the first variable. So we are writing here y because second one is missing from here. Again 1 and 2. Third variable is missing. Right here z. So how to solve it? This is x, y and z. We have to go for the determinant of order 2. What we will do? We will solve this determinant of order 2. This is minus 4 and minus 4. This is minus 8. The next is again solve the determinant here. This one next to 8 plus 4. This is 12. Solve this one. This is minus 4 plus minus 4 plus 8. This is again 4. This is 4. Right? So if we are writing it here, this is minus 8, the value of x, the value of y is 12 and the value of z is 4. What do you have to do? You have to take the highest common factor from here. Either you can take minus 4 or you can take 4, it's your choice. If I am taking minus 4 as a common from here, this is giving you minus 2, 3, sorry, positive 2, minus 3 and minus 1. Anybody can take 4 as a common from here. If you are taking 4 as a common, so inside we are left with here minus 2, 3 and 1. So this is your eigenvector. Fine. If you want to eliminate the common factor here, you can eliminate here. So the eigenvector corresponding to the value lambda is equal to 3, we are having here is 2, minus 3 and 1, or you can also say minus 2, 3 and 1. It's your choice. Fine. The same method we can follow for to find the eigenvector corresponding to the value lambda is equal to minus 5 and 6. I can explain one more here. If we are supposed to calculate the eigenvector corresponding to the value lambda is equal to 6 here. So what we have to do, firstly we have to calculate a minus lambda I. A minus lambda I, we had already calculated, I had just erased it. This is minus 2 minus lambda, minus 4 and 2. This is minus 2, 1 and 2. This is 1 minus lambda, this is 4, 2 and 5 minus lambda. Just replace the value lambda is equal to, we are calculating for lambda is equal to 6. Just replace the value lambda is equal to 6 here. We will get here the equation as minus 8, minus 4 and 2. The next will be 2. Replacing the value lambda is equal to 6 is minus 5 and 2, 4, 2 and minus 1. Fine. X. The value of x will be x, y and z. Fine. I have just replaced the value lambda is equal to 6, lambda is equal to 6 and lambda is equal to 6. Now just multiply the equations. We will get here minus 8x minus 4y plus 2z is equal to 0. The second equation will become 2x minus 5y plus 2z is equal to 0. The last will be 4x plus 2y minus z is equal to 0. Again, all the equations are distinct. You can pick and choose any of the two equations. I am taking again the bottom two equation. The rule is 2, 3, 1 and 2. 2 means the second variable. Pick the coefficient of second one. Second variables are coefficients are minus 2 and 2. It means we have chosen y. Coefficient of y will be minus 5 and 2. Right here minus 5 and 2. The next will be the third variable. Third variable is z. So the coefficient of z are 2 and minus 1. This is 2 and minus 1. Now this is your first variable. First variable is x. Take the coefficient of x, which is 2 and 4. This is 2 and 4. 2. 2 means again the second coefficient. This is minus 5 and 2. The same rule will be followed, which we have discussed. 2 means the second coefficient. 3 means the third coefficient, third variable. Which one is missing? First one, right here x. Now which one is missing here? Y. First variable, second variable. Which variable is missing? Z. So right here Z. Simplify it by taking the determinant only. Take the determinant 5 minus 4. This is 1. Y, which is 8 plus 2. 8 plus 2. This is 10. And the last will be Z here. This is 16. So similar. So this is the eigenvector corresponding to the this matrix corresponding to the eigenvalue, which is lambda is equal to 6. So there are the different more questions which we can simplify. Like we can have distinct eigenvalues as in the previous question. We can also have the similar eigenvalues. Corresponding to the similar eigenvalues, we can also calculate the different eigenvectors. So we have studied the method to calculate the eigenvalue and eigenvector. Now the question arises, what are the applications? Why we are studying it? Where we are actually using it? So these are some applications of eigenvalues. Eigenvalues are used to determine the stability analysis in control theory. The second most common and which the student have studied in physics also. The eigenvectors are studied in quantum mechanics also. It is also used in the preparing car stereo. The vibration which is coming out in the car stereo, it is actually calculated by the eigenvalue and eigenvectors. The another oil companies where the oil are reserved can be calculated by eigenvalue analysis. And another, this is the most common, face recognition. This is the eigenfaces. Can also be studied by eigenvalue and eigenvector. Even this is also used in making the bridges also. The bend in the bridges can studied by your eigenvectors. This also described. There are more application in the real life which I have not mentioned even here. So this is the brief of the eigenvalue and eigenvector. Thank you very much.